Welcome to the presentation on Adaptable and Divergent Synthetic Benchmark Generation for Hardware Security. I'm Sarah. I'm a PhD candidate at the Florida Institute of Cybersecurity Research at the University of Florida. Now, before we dive into the technicality of the framework, let's look into the scope of the work, and that is hardware security. Hardware security are the field of research that works on the security of hardware designs, and it both includes the protection schemes and the threats. The first protection scheme I'm going to mention here is hardware obfuscation, which is inserting some additional logic into a circuit in order to make it unusable unless a certain key or unlocking pattern is given in the inputs. An example of the threat or attack that we discuss in hardware security is hardware Trojan, which is some malicious circuit modification or insertion of some malicious circuitry into a design by an adversary to make the IC unusable or introduce a kill switch or even sometimes to leak some information. Another threat is side channel analysis, where an adversary can snoop into the power lines to leak secret information from inside of this IC. Now let's look into the problems these hardware security features are facing right now. The maximum of the work that has been done in these fields are being validated using very old benchmark circuits. And we have looked into some very popular, most cited papers in obfuscation and attacks. And all these papers have been published between 2008 and 2020. We have found that more than 40% of them are using ISCAS 85 benchmark source, which was already more than 3 decades old by the time of using. And other 30% are using ISCAS 89 or MCNC 91 benchmark suite. Now, the problem is these benchmark suites were developed in the 80s for EDA or CAD tool development, and they were wonderful back then, and they were adopted in many other fields later on, but they were not developed for hardware security purpose. What it means is they don't contain any asset to be protected, or everyone knows their designs. Sometimes they are so familiar that people can look into the circuit and know that, okay, there are some additional gates in there. They don't actually represent the present scenario of an industrial design. Another reason for that is the size. All these benchmarks are very small. They were pretty good when they were developed. And if you look into the Moore's law, the number of transistors in an IC increased exponentially in last 3 decades. So the benchmark that represent the circuits back then holds very little similarity with the industrial design nowadays. And another problem is the quantity. So if you look into the data-driven analysis like machine learning, there needs millions of samples to be validated. But if you look into the benchmark that we have, it's merely few hundreds, and they don't actually provide all the samples that is needed. Neither they provide all the variation that is required to cover all the corner cases in those kind of data-driven analysis. And the only solution for this one is having a synthetic benchmark tool, which can generate as many benchmark you want, as large you want, and they will be new. So the IP would be uh, asset in here. So a synthetic benchmark can support all these three issues that we are having right now in the present benchmark suite. So let's look into the existing synthetic benchmark tool. The synthetic benchmark tool was first introduced again in the 80s in order to support the needs for the CAD tool development. and they have been adopted in many works further, like in floor planning or placement and route and all those fields and FPGA, but they have not been actually adopted in hardware security before. So the tool that's available, the first one in synthetic benchmark tool is a CSARC tool, and this one takes a circuit and then translates it into a statistical file called stats file. And then this stats file can be passed through another tool called cgen that the same authors have provided, which can translate it back into a circuit format. And there are some randomization in the generation process which would make the new circuit different than the original one. But if you do some modification by hand, you can get a new circuit. But the thing is, when the tool generates the stats file, it's a complex collection of data that not all the data is explained in literature. Also, it's not very possible for a human to modify it by hand that works properly to generate a circuit. So there's a very limited kind of modification you can do to make the modified stat file, not a lot. And as a result, the resulting circuit will be somewhat similar to the original circuit. So this synthetic tool worked for CAD development, but it has limited usefulness for the hardware security purposes because it was not intended for doing so. Now, our hypothesis is if we place the benchmarks along the axes, where the axes can represent any functional or structural parameters of circuits, we can find that the existing benchmark forms a cluster. A target would be to generate synthetic benchmarks that would not form a cluster and would be spread to the entire space more efficiently, which means the benchmarks would provide more difference or variation in the characteristics and parameters than the existing benchmarks. Now, with that, let's move on to the outline of our framework. It starts with the CSARC tool and the statistical files that it produced. Along with that, we have some user inputs like number of gates in the resultant benchmark and the delay and total number of primary inputs and primary outputs. Also, the maximum allowable fan-in and fan-out of gates in the resultant design. With the user input, we would have a database of previously generated benchmark, and, and all this data is provided into an integer linear optimization tool. The target of this optimizer is to find the most different circuit structure that is possible. Optimizer returns another stats file, which is then converted into a circuit with our custom generation tool. The generation tool takes input for the logic choice, which can be random or any heuristically driven logic assessment. And also, this new optimized stat file is included into the database to be used in the future generation of synthetic benchmarks. Now, if we look into the depth, this part of the framework I have already explained, so I will skip. And let's move on to the statistical files and what these files contains. The circuit is represented in this graph where the gates are placed by their information arrival delay or how close to they are with the inputs. The first level is the delay level 0, we are the inputs and rest of them are the gates. And we define these levels as depths, and if 1 is the input and 2, 3, 4, they are gates. And nodes represent the number of gates in per depth, and for this case, node first element of node means the inputs and the rest are gates. The second data we have is number of internal inputs that come to that specific depth. The next one is the number of internal outputs that driven from each of these steps. The next one is the number of primary outputs that pulled from the each step. Next, we have the edge, which represents the number of wires of certain length in the entire circuit, where we can see 0 means there are no wires of length 0, and 13 there are 13 wires that have a length of 1. And the last data we have is number of gates with certain number of fan out of internal outputs. Here we have two gates with no fan out that represents these primary output gates. So these are all the data that's represented in the stats file, and you can also visualize this data by a bar chart. And this necessarily represent the structure of this entire design. So now let's move into the linear optimization part in the framework. This is the optimization equation that we use to make the synthetic benchmark as different as you can get. The first part of the equation represents the distance between the synthetic benchmark and the reference benchmark, and it has been summed up for each reference benchmark. And the second, this part represents summing up the differences along all the axes. Now, we're showing only 3 axes here for visualization purpose, but in actual, the total number of axes are the total number of parameters that we are using times the total number of depth. So in here, we have used the 6 parameters that I have shown in the statistical file, and the depth can be 10, 20, 30, or higher. And so we'll increase the number of axes. And this optimization equation is subject to constraints and bounds, where the constraints includes user-specified constraints and node distribution related constraint, primary internal input and output related constraints, and others. And though we have avoided explaining the constraints in this presentation for brevity, we actually had to implement more than 25 constraints to make the optimization end up in a valid circuit. Now let's move on to the self-referencing or the recursive part of the framework. So this actually ensures that the synthetic benchmarks are different from each other along with being different from the reference benchmark. And when we generate the first synthetic benchmark, it is generated from the distances from the reference benchmarks. When we generate the second benchmark, it includes the first one in its references. And when we generate a third one, it would count the previous 2 benchmarks as references. So, and it will make sure that the synthetic benchmarks are not being generated in the same positions again and again and do not form a cluster. Now, it is very useful when all the reference benchmarks are clustered. So what happens is the first benchmark is placed very distant from the cluster, and the second one is in distance from the first one and the reference one. So in each step, the placement of the synthetic benchmark is very adaptable with the already generated ones. And as you keep generating more and more benchmark, they makes the synthetic suit very divergent. Now let's look into the last part of the framework, that is a custom generation tool. This tool translates the statistical files back into the circuit format or gate level netlist format, and it takes input of the logic choice, which can be random or can be heuristical like controllability or observability driven logic, or one can choose just NAND only design or lookup table designs. And the synthetic benchmark that's getting generated can be library independent ISCAS format, or it can be in a format that's mapped with Cadence library, which you can use in any CAD tool or commercial tool. In our experimental setup, we use the CSARC tool, we use MATLAB for integer linear programming, and the custom generation tool is developed in Java platform. For testing and analyzing, we used commercial tools, Design Compiler and Tetramax from Synopsys package, and we used ABC, CSARC, and SAT tool as open source research tools. As reference, we used ISCAS 8510 benchmarks, and for a sample, we synthesized 12 benchmarks. In the first analysis, let's look into the structure. The first plot here, upper two row, represents the ISCAS 85432 benchmark and a synthetic benchmark that is generated just based on that circuit. Now, if we look into the structure, we can see that this structure, the synthetic benchmark, is very much different from the reference benchmark. And this was generated with arbitrary 500 gate, which is larger than the reference, but structurally it's very different than the 432 benchmark. The lower two row represent the benchmarks that we generated with comparing with the entire ISCAS 85 benchmark suite. Now the first row here represents an average distribution of the reference circuits, and the resultant synthetic benchmark with 1000 gate has been is represented in the lower row. Now look into the resultant results, how they look for the benchmarks. We have placed reference and synthetic benchmarks along the axes which represent observability, controllability, CNF clauses. We can see that original ISCAS benchmarks, the blue dots are placed as a clustered, where the synthetic benchmarks are spread along the space. And we have done some principal component analysis and placed the benchmark along the three primary components, where we can see the red dots are more divergent or having more differences in qualities than the original reference circuits, the blue dots. Now let's look into another feature which relates to the controllable feature and the observable parameter. We have looked into all the circuits and found that the controllability and observability increases with depth, so does CNF clauses and CNF literals. Now, depth is a parameter that the synthetic generation tool takes as an input, and controllability and observability directly relates to the resiliency of a circuit against certain obfuscation attacks like key sensitization attack. With increase of controllability or observability value, it means the circuit is more resilient to such attacks. And the number of CNF clause and CNF literals directly relate to the resiliency of the circuit to the very popular SAT attack. So a designer can choose a larger depth to make the synthetic benchmark more resilient to SAT and key sensitization attack if they want. Now this is a sample analysis of the applicability of our benchmarks in security research. For the first one, we have done the Trojan detectability test, where we inserted a certain number of Trojans and tried random simulation to detect the Trojan. In case where we inserted only a single Trojan, 4% of simulation detected the Trojan in case of ISCAS benchmark, while less than 1% simulation could detect such Trojan in synthetic benchmark. In case where we inserted 5 Trojans, we have seen that for ISCAS benchmark, more than 10% simulation could detect the Trojan, while Around 4% of the simulation could detect the Trojan for synthetic benchmark. This means the synthetic benchmark suit is providing more challenge for the Trojan detection scheme. Next, we have done the obfuscation breakability analysis, where we have obfuscated randomly both the SCAS and the synthetic benchmarks with 256-bit key and ran SAT attack to break the key. From the data, we can see the synthetic benchmark suit is providing more challenge to the attack than the original SCAS suit. If we look into the scalability of the optimization process, we can see that the time increases with depth, but after certain depth, the times become more like saturated or sometimes getting lower with the depth. And the time does not vary much with the number of gates in the design. Now, this is a result of two complex situations. One is the optimization complexity, which is directly related to the number of variables and equations, and it increases exponentially with the depth. Another is the design complexity, which is related to the number of gates per depth, and it decreases with the depth. For both of these curves, the resultant time looks like this. Now, in this presentation, we have outlined the problem and we have detailed our framework. We have explained what our experiments did and what we have found as a result. We have already published our tool as open source in Trust Hub website. And we believe in future we can make the optimization more scalable. We want to combine the logic and the structure in a single optimization, and we were looking forward to include the sequential designs also in the reinforcement generation process. That was all from the presentation, and thank you for being with me.